What's up, everybody? My name is Eric. Welcome to my channel, Eric the Tutor. Today, we're going to be continuing our discussion on carbohydrate reactions. And we're going to talk a lot about oxidation and reduction. So let's go ahead and jump into an example. Here, I went ahead and drew our beta and alpha anomers of glucose. So we can see here, this is our beta anomer, and this is our alpha anomer. Now, which one do you think we see more in equilibrium? Well, we see the beta anomer at approximately 64%, and we see the alpha anomer at approximately 36%. Why do you think we see more beta than we do alpha? Well, that's because the beta exists in the equatorial state, and we know that's not as sterically hindered as our alpha anomer down here. So if we react our open-chained glucose molecule with the aldehyde with something called Tollen's reagent. Tollen's reagent is an oxidizing agent. So Tollen's reagent looks like and we're going to also react that with some OH minus. Now, I'm not going to show the mechanism for all of these, but I'll go ahead and show the mechanism for Tollen's reagent. The first step is the OH minus is going to come and hit our carbon there. That's electrophilic. It's going to push up the electron density, and we're going to get something that looks like, here's R to represent the rest of the glucose chain. We have R, our new O minus, we have our hydrogen there, and our new OH group that just added. Now we have some AgNH3 2 floating around, so this O minus here can go and hit our AgNH3 2. So when it does that, we're going to get something that looks like R, here's our O, Ag with NH3. Awesome. And we have our OH up here and hydrogen here. Well, if another OH minus is floating around, here's our OH minus. The OH minus can come and grab our hydrogen here. This can form a double bond right in there and kick this group right on out of there. So then let's see what we get. We get R, double bond O. Looks like we get a carboxylic acid. Now, interestingly enough, because there's a lot of OH minus floating around in solution, we're not done quite yet. We're not going to get the carboxylic acid all the way. So this OH is going to come and grab this hydrogen, and it's going to push that electron density onto our oxygen. This is going to give us something that looks like that. So we're not going to quite get the carboxylic acid, but this was oxidized, right? We started with an aldehyde, and we went all the way up almost to a carboxylic acid. Let's go ahead and look at another reagent. What if we reacted something with this open chain? We're going to call this one Benedict's reagent. Benedict's reagent involves copper. Okay, and like I said, I'm not going to show the whole mechanism for this one. I'm just going to show here that this one does something similar to the Tollen's reagent, except in this case, we expect to see it go all the way, and we expect to see that carboxylic acid. So here's our R group, here's our C double bond O, and here is our carboxylic acid. So it was much stronger, and it took it all the way to our carboxylic acid. Great. Let's go ahead and see another example. We're going to keep this going with our oxidation here. So let's go ahead and think of another oxidizing agent. We could put Br2 in water. And this is going to do the same thing like we saw up here. We're going to get R, C double bond O, and an OH. Now, none of these other OHs on our glucose will be affected. Br2, this is a mild oxidizing agent. So it only affects the carbon here at our aldehyde carbon, okay? It oxidizes that carbon, leaves everything else alone. We could, however, have something a little bit stronger like HNO3. What if we had HNO3? What do you think we're going to get? Well, in this case, I'm going to actually draw out our glucose molecule so we can see what we get. So here's this. We still expect to see this is a strong oxidizing agent. HNO3 is a strong oxidizing agent. So we expect to see this to be a carboxylic acid just as before. All these OHs are going to be the same. So here is this. None of those are going to be affected. However, our CH2OH that was right here, CH2OH, that's going to be affected, and we're going to end up having a carboxylic acid coming off of there. So we can see that HNO3 was much stronger, and it was able to oxidize 2 different locations to give us carboxylic acid. Great. Let's go ahead and now transition over to reducing agents. A common reducing agent that we would expect to see is NaBH4. Now, NaBH4 is going to take our aldehyde, and instead of going further to our carboxylic acid, we're in a sense going to be going backwards, and we're going to be heading in the alcohol direction. So it's going to take this aldehyde here, and it's going to make it an alcohol. It's going to take that C double bond O and convert it, add some hydrogens there. Some hydrogens from our NaBH4 are going to directly attack this carbon twice, and it's actually going to give us a CH2OH. It's going to give us a primary alcohol. If we had a ketose, it could do the same thing. If we had a ketose at carbon 2, it would also change that location. It would change that carbon to a OH, and it would be both in the R and the S stereochemistry. Great. The last thing I want to do, I want to talk about the difference between esterification. So here is esterification and reacting with an alcohol. Say we did CH3, CH2, OH. Okay? When we do esterification, we're typically going to be using a carboxylic acid or carboxylic acid derivative. So if we reacted this beta anomer of glucose with, let's say, a anhydride. Let's go ahead and say we had an anhydride. Then we'd expect every single location that has an OH to become an anhydride. So we'd expect this location, all of these with OHs will ultimately end up having an anhydride functional group coming off of it. So we get something that looks like this. Here is our C. Now it's only going to be part of our functional group here. So here we have we react our anhydride, and we're going to actually get an ester. So we're going to get an ester with the rest of the group coming off. So here is that group right there, CH3. Now this same group, I'm going to head and call it Y. All of this will be coming off of here, 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 and there. All of those will have our ester groups. That's what esterification is going to do. Now, if we reacted instead with an alcohol, such as CH3, CH2OH, it's not going to affect all of the carbons. It's only going to react specifically at our anomeric carbon, where we could either have the beta or the alpha anomer. In this case, if we do CH3, CH2OH with this, we're going to get something that looks like all of these groups will stay the same. These groups will not be affected. However, what will be affected is this alpha anomer, right? So now we will have OCH2, CH3. So we essentially added an alkoxy group to this molecule. So this could be in the alpha or beta forms. All right, so this concludes our discussion on carbohydrates. We talked about many different reactions, and we concluded here with oxidation, reduction, esterification, and adding an OCH2CH3 group to specifically our anomeric carbon. Thanks for tuning in, guys. I'll see you next time.